and foremost, let us introduce ourselves. My name is Nur Izzah Insyirah binti Syaiful.
Hi, my name is Nur Wakilah Fatia binti Akil.
Hi, my name is Nur Araudah Aina Fakiah binti Ayub.
Hi, my name is Nik Nurasmira binti Asari.
Without further ado, let's get into the introduction. Hollow concrete bricks are widely used in the construction industry because they are strong, durable and easy to install. However, conventional concrete uses a large amount of natural aggregates and cement, which can cause environmental pollution and reduce natural resources. To support sustainable construction, our group replaced 5% of the natural coarse aggregate with crushed waste cockle shell. This mini project supports SDG 9. The project encourages sustainable infrastructure by reducing construction waste and promoting innovative engineering practices by using recycled materials. It also provides sustainable solution for civil engineering while encouraging teamwork, practical learning, and knowledge sharing among students. In this mini project, 5% cockle shell was used as a sustainable replacement material in the production of hollow concrete bricks. The aim was to investigate whether the additional cockle shell could maintain or even improve the workability, compressive strength, and service life of the concrete while reducing environmental impact.
Next, I will explain the methodology used in this study. The first stage is material selection and preparation. First, waste cockle shells were collected from restaurant Gerang Bakar Starbucks. The shells were then washed thoroughly using water and a mild cleaning agent to remove any dirt, salt, and organic matter that could affect the quality of the concrete. After cleaning, the shells were left to air dry overnight. They were crushed into small pieces using a hammer. Finally, the concrete materials were prepared. Ordinary Portland cement, sand, coarse aggregate, water, and 5% of crushed cockle shell were selected according to the concrete mix design. All materials were weighed accurately before the mixing process. The second stage is the concrete mix preparation. All materials were first weighed according to the mix design. The mix consists of 1.3853 kg of cement, 2.3332 kg of sand, 4.1214 kg of coarse aggregate, 0.6927 kg of water, and 0.2169 kg of crushed cockle shell. Next, the cement, sand, coarse aggregate, and crushed cockle shell were dry mixed until the materials were evenly distributed. After that, water was added gradually while the mixing continued. The concrete was mixed until a uniform and workable consistency was achieved before being placed into the mold. The third stage is the brick fabrication process. Before casting, a thin layer of grease oil was applied inside the plywood mold to prevent the concrete from sticking and to make demolding easier. Next, the fresh concrete was poured into the mold. The mold was then compacted using a concrete vibrator to remove trapped air voids and improve the density of the brick. After compaction, the top surface was leveled using a trowel. Once the concrete had gained sufficient initial hardness, the brick was removed from the mold. The specimens were then cured in water for 7 days. The final stage is testing and evaluation. Before conducting the compression test, the dimensions of each brick, including the length, width, and height, were measured. The weight of each brick was also recorded. Finally, the bricks were tested using a compression testing machine. During the test, the maximum load at failure was recorded and used to calculate the compressive strength of the concrete brick.
Before curing period of 7 days, our brick sample had a weight of 2.671 kg, which increased slightly to 2.679 kg after curing. This small increment shows that the brick absorbed a small amount of water during the curing process, making the cement gain more strength. The figure attached shows the calculation of compressive strength, which is by subtracting the gross area and hollow area to get net area value. The brick has reached an ultimate load of 230.4 kN during the compression test, resulting 13.378 MPa of compressive strength. As a result, this indicates that the brick had good load-bearing capacity and it is able to withstand a high compressive force before failure. Overall, the results indicate that replacing 5% of cockle shell into the concrete mix can produce a high compressive strength hollow brick.
In this discussion, we evaluate the physical and environmental effect of using 5% crushed waste cockle shells as a coarse aggregate replacement in hollow concrete bricks, focusing on mechanical data, liability observation, and sustainability. For mechanical performance, after a 7-day curing period, our bricks achieved an ultimate load of 230,400 newtons and a compressive strength of 13.378 megapascal. This outcome demonstrates that a low replacement percentage is sufficient to successfully maintain the structural performance of the bricks. These findings strongly support past technological literature, which indicate that low-level replacement ranging from 5% to 20% provide the most optimal mechanical performance. This high strength comfortably surpasses the standard 3.5 to 5 megapascal required for non-load bearing units. For the strength factor and characteristic, the high calcium carbonate contents of approximately 99% inherent in the cocker shells contribute directly to the hardness and rigidity of the concrete matrix. The rough and ribbed outer surface of the crushed shell improve the bond with the cement paste, resulting in the superior mechanical interlocking. This enhanced internal bonding helps reduce internal slip and effectively delays the formation and growth of the microcracks under compressive loads. Although the flat, flaky and angular geometry of the shells can create internal voids, the height strength of 13.378 megapascals proved that the overall mechanical performance was not negatively affected. Aligning with SDG 9, this project promotes a circular economy by upcycling zero-value food waste from local business like restaurant Kerang Bakar Starbucks, preventing it from entering landfills. Furthermore, replacing 5% of natural gravel directly reduces the ecological impact, energy use, and carbon emission associated with stone quarrying and material transport. Finally, our laboratory observations show that manually crushing the shells with hammer product angular and flaky particles, while the texture surface improving bonding, the flat geometry creates a risk of trapping micro air voids underneath. Therefore, proper compaction using a mechanical concrete vibrator was absolutely essential to remove trapped air, increase concrete density, and ensure an even distribution of materials.
In conclusion, this mini project successfully achieved its objective by evaluating the use of 5% crushed waste cocker shell as a partial replacement for coarse aggregate in hollow concrete bricks. The fabricated brick achieved an ultimate load of 230.4 kN and a compressive strength of 13.378 MPa, showing that the replacement maintains satisfactory mechanical performance. The high calcium carbonate content and rough surface of the cocker shells improve the bond with the cement paste, contributing to the strength of the brick. In addition, reusing waste cocker shells helps reduce food waste, conserve natural aggregates, and support Sustainable Development Goal SDG 9 by promoting sustainable construction practices. However, this study was limited to one replacement percentage, one brick specimen, and a 7-day curing period. Therefore, future studies should investigate different replacement percentages and conduct additional tests such as water absorption, durability, density, and a 28 compressive strength to provide a more comprehensive evaluation. Overall, 5% crushed waste cocker shell has the potential to be a practical, sustainable, and environmentally friendly alternative for producing hollow concrete bricks.
This project provided many benefits to our group. First, it improved our practical skills in producing hollow concrete bricks. We learned how to prepare cockle shells, measure materials accurately, mix concrete, cast the bricks, cure them properly, and carry out the required laboratory tests. Secondly, this project enhanced our understanding of sustainable construction materials. We discovered that waste cockle shells can be reused as a partial replacement for natural coarse aggregate, which helps support sustainable construction practices. Third, the project promoted environmental sustainability. By using discarded cockle shells, we reduce waste disposal and help conserve natural aggregate resources, contributing to a greener construction industry. Fourth, we developed our teamwork, communication, and technical reporting skills. Every group member participated in the laboratory work, data collection, report writing, and presentation preparation. Finally, this project strengthened our problem-solving and critical thinking skills. We analyzed the performance of the concrete bricks with cockle shell replacement and evaluated whether the sustainable material could be used effectively in future construction projects. That is all from us. Thank you.